data representation, data processing, elementary programming principles, and system development. Introduction. In Form 1, we learned that the most commonly used computers today are digital computers. We also learned that data and instructions cannot be entered and processed directly using the natural language, but they must first be converted and transmitted in form of electric pulses represented by two distinct states, on and off. The on state may be represented by a 1 and the off state by a 0. These are the only two states that a computer can understand.
The on and off can be converted to a digital signal and can be represented graphically as a square wave as shown below.
In digital computers, data is handled by peripheral devices in form of electronic circuits, magnetic form, and optical form. We have already seen the representation of digital signals in form of electric pulses. Just like in digital circuits, the presence of a magnetic field in one direction on a magnetic media is interpreted as 1, while the field in the opposite direction is interpreted as 0. In optical devices, the presence of light is interpreted as 1 and the absence of light is interpreted as 0. The following figure shows a laser beam reflected from the lands and pits, and when the red arrow falls on a land, it's reflected, and it's interpreted as a 1, and when the blue arrows fall on a pit, it's not reflected, and this is interpreted as a 0.
Due to the complexity of natural language, computers do not understand or process human language directly. The human language must be first converted to a language the computer understands, called the machine language, before it can be processed. This language is in form of ones and zeros. The following illustration shows the binary equivalent of the word the binary.
Example, the word then is recognized by the computer as follows. In the previous lesson, we learned that computers can only understand machine language, which is in form of zeros and ones. The zeros and ones are the binary digit, also known as bit. A bit is the smallest unit of data on a binary computer, which can either be a 0 or a 1. A group of 8 bits makes byte. A nibble is a collection of 4 bits, otherwise also known as half a byte. A word is a group of 16 bits or more. Word length is the number of bits in a word. Example, a 16-bit word and a 32-bit word have a word length of 16 bits and 32 bits respectively. In digital computers, data is handled by peripheral devices in form of electronic circuits, magnetic form, and optical form. Introduction. Although computers understand binary numbers, complex types of data such as sounds and pictures can be represented using higher number system to reduce the long strings of binary codes that take a lot of memory and processor time. The higher number system reduces streams of binary into manageable form, which helps to improve the processing speed and maximize memory usage. Number system is a set of symbols used to represent values with a common base. Decimal number system. You've been using the decimal, which is base 10, numbering system for so long that you probably take it for granted. When you see a number like 123, you don't think about the value 123. Rather, you generate a mental image of how many items this value represents. In reality, however, the number 123 represents... When you write decimal base 10 numbers, we use a positional notation system. Each digit is multiplied by an appropriate power of 10 depending on its position in the number. We note in the decimal number system, there are 10 possible values that can appear in each digit position, and so there are 10 numerals required to represent the quantity in each digit position. The decimal numerals are the familiar 0 through 9. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In a positional notation system, the number base or the base of a number is also called the radix. Binary number system. Binary number system only has 2 digits, that is 1 or 0 as earlier discussed. The binary number system is also a positional notation numbering system, but in this case, the base is not 10, but instead 2. The following is an example of a binary number. Each digit position in a binary number represents a power of 2. For example, considering the following binary number 11010 base 2, the positional notation of the above binary number can be presented as follows. Starting from the right, the position value of 0 is 2 to the power of 0. The position value of the next 0 is 2 to the power of 1. The position value of 1 is 2 to the power of 2. The position value of 0 is 2 to the power of 3. The position value of 1 is 2 to the power of 4. The position value of 1 is 2 to the power of 5. Note that place value of binary numbers goes up by in factor of 2 from right to left. The rightmost digit is the least significant bit, and the leftmost bit is the most significant bit. Octal and hexadecimal number systems are higher number systems than decimal and binary number systems. Instead of transmitting in digits of ones and zeros between devices, the data can be encoded as octal or hexadecimal to improve transmission efficiency. A single octal or hexadecimal digit encodes more than one binary digit. This is automatic data compression, hence storage media can save space. Hexadecimal number system. This number system uses 16 numbers ranging from 0 to 9 and letter A to F, representing numbers 10 to 15 respectively. Place value of hexadecimal numbers goes up in factors of 16. Hexadecimal numbers have a base or radix of 16. For example, 47 to the base of 16. It is known as base 16 system. The following are some additional examples of hexadecimal numbers. So far, we have introduced the basic concepts of 4 number systems we have learned. Now, we shall have a detailed look of how we can convert numbers from one system to another. Conversion of binary to decimal. Converting a number from binary to decimal is quite easy. All that is required is to find the decimal value of each binary digit position containing a 1 and add them up. Let's convert to decimal the binary number 101101 to base 2.
Binary conversion to decimal. This is binary, it is in this form of base 2. We want to convert it to decimal, which is base 10. Our method, we are going to go direct to multiply values to base 2 times the binary values multiplied by the place values of the digit. So we have, we start with the first one here, we say 2 to the power 0. This one is at the place value of 2 to the power 0, starting from the right hand direction. So it is 2 to the power 0 times 1 plus 2 to the power 1 times 0 plus 2 to the power 2, the third place value, times the binary number digit is 1 plus the next one is 2 to the power 3 times the place value is 1, then plus the fourth place value is 2 to the power 4 times the binary digit is 0, plus the last one is 2 to the power 5 for the place value times the binary digit value is.
To convert a binary number to decimal number, we proceed as follows. Write the place values of each digit starting from the right-hand side to the left-hand side. Then multiply each digit by its corresponding place value. Add up the product. The answer will be the decimal number in base 10. Convert the following binary numbers to decimal numbers. Introduction. In the last lesson, we learned how to convert binary numbers into decimal numbers, and in this lesson, we will learn how to convert the decimal numbers into binary numbers. There are two methods used for converting a decimal number to binary. The first method is successive or long division method. The second method is using the place value method. Example 1. Let's convert the decimal number 156 to the base of 10 to binary. Write the decimal number as the dividend inside an upside down long division symbol. Write the base of the destination system, in our case 2 for binary, as the divisor outside the curve of the division symbol. Then write the integer answer, which is a quotient, under the long division symbol and write the remainder 0 or 1 to the right of the dividend. Continue downwards, dividing each new quotient by 2 and writing the remainders to the right of each dividend. Stop when the quotient is 0. Starting with the bottom remainder, read the sequence of remainders upwards to the top. You should have 1, 0, 0, 1, 1, 1, 0, 0. This is the binary equivalent of the decimal number 156. Example 2. Let's now convert the decimal fraction 156.625 to the base of 10 to binary. Step 2. Convert the fraction part, which is 0.625 to the base of 10 of the decimal number, to binary. Disregard the whole number part of the previous result. In this case, 1. Multiply the fraction part, which is 0.25 of the product, by 2 again. The whole number part of this new result is the second binary digit to the right of the point. We will continue with this process until we get a 0 as our decimal part, or until we recognize an infinite repeating pattern. The second binary digit to the right of the point is a 0. So far, 0.625 is equal to 0.10 to the base of 2. Disregard the whole number part of the previous result. Note that this result was 0.50, so there actually is no whole number part to disregard in this case. We therefore multiply 0.50 by 2 once again. The whole number part of the result is now the next binary digit to the right of the point. The third binary digit to the right of the point is a 1. So now we have 0.625, which is equal to 0.101 to the base of 2. Introduction. To convert a decimal number to binary using the place value method, write down the place values of the binary in factors of 2 up to the value immediately larger or equal to the number being considered. For example, using the place value method, let's convert 254 to the base of 10 to binary. Step 1. Write down the place value up to 2 to the power of 8, which is 256, which is the number immediately larger than 254 because 2 to the power of 7, which is 128, is smaller than the 254. Step 2. Starting from the left, subtract the place value from the number being converted. If the difference is a positive number or a 0, place 1 in the binary digit row. If the difference is negative, place a 0 in the binary digit row as illustrated in the table below. Note that when the difference is negative, the number is carried forward to the next lower place. Step 3. The binary equivalent of 254 to the base of 10 equals 0, 1, 1, 1, 1, 1, 1, 1, 0 to the base of 2. Other number conversions are conversion of binary and decimal numbers to octal and hexadecimal numbers, conversion of octal numbers to hexadecimal numbers, conversion of octal and hexadecimal numbers to binary and decimal numbers. Introduction. This is a type of representation where a character, be it a letter, number, or symbol, is represented by a group of bits. The most commonly used coding schemes are binary coded decimal, BCD, extended binary coded decimal interchange code, EBCDIC, and American Standard Code for Information Interchange, ASCII. Binary coded decimals, BCD. It's a 4-bit code used to represent numeric data. For example, 7 is equal to 0, 1, 1, 1 to the base of 2. It is used in simple electronic devices such as calculators, watches, and microwave ovens. Its major limitation is that it can only be used to represent a maximum of 16, which is 2 to the power of 4 characters. Extended Binary Coded Decimal Interchange Code, EBCDIC. This is an enhanced form of the standard BCD, and it's an 8-bit character coding system that represents up to a maximum of 256, which is 2 to the power of 8. It's mostly used in computers. For example, the EBCDIC representation of the letter A is 1, 0, 0, 0, 0, 0, 0, 1 to the base of 2. American Standard Code for Information Interchange, ASCII. This is a 7-bit coding system that can represent a maximum of 128, which is 2 to the power of 7 characters. Due to the limitation of numbers of characters that could be represented, an 8th bit was added to enhance ASCII into an 8-bit coding system. The maximum number of characters increased to 256, which is 2 to the power of 8. In computers, we can represent signed binary numbers by prefixing an extra sign bit to a binary number. In decimal numbers, a signed number has a prefix of positive for a positive number and negative for a negative number. In binary, a positive number may be presented by prefixing a digit 0, and a negative number may be presented by prefixing a digit 1. For example, a 6-bit binary equivalent of 27 to the base of 10 is 0, 1, 1, 0, 1, 1 to the base of 2. To show there are only 5 possible additions in binary. First one is 0 plus 0, which equals to 0. 0 plus 1 equals 1. 1 plus 0 equals 1. 1 plus 1 equals 1, 0, read as 0 carry 1. And 1 plus 1 plus 1 equals 1, 1, read as 1 carry 1. There are 4 possible subtraction in binary. 0 minus 0 equals 0. 1 to the base of 2 minus 0 equals 1 to the base of 2. 1 to the base of 2 minus 1 to the base of 2 equals 0. 1, 0 to the base of 2 minus 1 to the base of 2 equals 1 to the base of 2. This means you borrow 1 from the next most significant bit to make 0 to become 1, 0 to the base of 2. The term complement refers to a part which together with another makes up a whole. In geometry, complementary angles add up to 90 degrees. In binary numbers, the ones complement is the bitwise not applied to the number. The bitwise not is a unary operator. That is, it operates only on one operand and performs logical negation to each bit. For example, the bitwise not of 1101 to the base of 2 is 0010 to the base of 2. The bitwise not of 0000 is 1111 to the base of 2. For example, using 8-digit bit binary notation, find the ones complement of 27 to the base of 10. Step 2. To convert this answer into an 8-bit binary notation, add zeros to the left as illustrated below. Step 3. Find the bitwise not of the 8-bit answer from step 2. Step 4. Therefore, the ones complement of 27 to the base of 10 using an 8-bit binary notation is 111001 00 to the base of 2. The main purpose of using ones complement in computers is to enable us to perform binary subtraction easily. For example, to get the difference in 7 to the base of 10 minus 4 to the base of 10, using the ones complement, we proceed as follows. The 2's complement of a number is obtained by getting the ones complement then adding 1. Step 2. To convert this answer into an 8-bit binary notation, add zeros to the left as illustrated below. Step 3. Find the bitwise not of the 8-bit answer from step 2. Step 4. Add 1 to the right-hand side of the ones complement of 7 to the base of 10. Therefore, example 2. Using 2's complement to work out 7 to the base of 10 minus 4 to the base of 10 in binary form. Step 1. You rewrite the problem. 7 to the base of 10 minus 4 to the base of 10 in brackets as 7 to the base of 10 in brackets negative 4 to the base of 10. Step 2. Convert 4 to the base of 10 into its binary equivalent. That is, the binary equivalent of 4 to the base of 10 is 000001 00 to the base of 2. Step 3. Find the ones complement of the binary number in step 2. The ones complement of 4 to the base of 10 is 111 111 011 to the base of 2. Step 4. Find the 2's complement of the binary number in step 3. Note that from the above, the 2's complement depicts a negative number.